Thank you. Yeah, I appreciate the opportunity to tell you all about what we don't know. Of course, that will take a very long time because there's a lot we don't know. I'm focusing on the part of what we don't know that I know the best, in the sense that the main drivers of supply and demand in the future, there are quite a few of them. Population growth, biggest. We also have to deal with reductions in supply in the sense of aquifer depletion and silt reducing the capacity of reservoirs. But I'm going to talk specifically about climate change and its potential impact on water supply. And climate change in the broadest sense. We're going to go talk about short-term issues as a window to understanding what we have to deal with over the long term. So back in the fall of 2010, the state was doing fairly well. We had had a fairly wet year, as you heard from the previous speaker. Most of the state was had benefited from a few tropical disturbances. East Texas was running a little dry. But we were concerned because a La Niña had developed in the tropical Pacific Ocean. La Niña being cold ocean temperatures, which affects where the tropical thunderstorm activity is, affects the global circulation, the temperature distribution, and has wide-ranging impacts across the globe. And unfortunately, Texas and the southern United States is one of the parts of the globe that are sensitive to El Nino and La Nina. So we were concerned about having a potentially dry winter. Turned out we had a dry winter, spring and summer, and the state had, by the end of September of last year, had its driest 12 months on record by a large margin. And really no part of the state had been spared from the drought. And then we were doubly concerned because another La Nina event was forming in the tropical Pacific. And so the potential was there for the drought to become even worse. And at present, however, things on the short term at least are looking relatively good. Now the recovery from the drought is progressing at different rates in different parts of the state. And so in East Texas, where you get lots of rain, 40 to 60 inches of rain a year, a few months of normal to slightly above normal rainfall has proven to be enough to replenish soil moisture, allow stream flows to recover, fill most of the reservoirs. Whereas in West Texas, 6 months of near normal rainfall is only about 5 or 10 inches of rain, which is barely enough to get the soil wet. And at this point, things are primed to produce significant runoff if we get additional rain during the traditionally wet months of May and June. But at present, this is the basic single picture of the drought in Texas. It's now quite variable, ranging from extreme to exceptional drought in parts of West Texas to no drought at all in some parts of East Texas. So, the question I want to address first is, why is it that we can have 2 years with the same thing in principle driving our weather, but one of them produces a close to catastrophic drought and another one produces a wet winter? And so describe an experiment that we've done. Actually, I haven't done it. Somebody else did it, but thank you for doing it. You take a computer model of the atmosphere, the same sort of model that's used to forecast the daily weather. And of course, if you run a model of the weather, it started off with realistic starting point. It'll match what actually happens pretty closely for the first few days, and then as time goes on, it gets worse and worse as a match to the weather. So after a week or so, you know not to trust the forecast, and that of course applies to what you see on TV as well as what comes from the model. But in principle, if the model is working properly, and if the relationship that we've observed between La Nina conditions and dry winters in Texas is a real relationship, then the computer model should, on average, produce a dry winter if you plug in a La Nina sea surface temperature pattern. So that's the basic idea of this experiment, actually looking at the ocean temperature patterns since 1950 and running the model for 54 years. And of course, if you run it, the weather day to day is not going to match what happened, but presumably, if the model's a good one, the statistics will match. And then you can run it again with a slightly different starting point, and again, statistically it should come out the same, but there's going to be variation that depends upon what sort of weather actually happens day to day and week to week. So with this sort of experiment, we can determine two things. We can tell how much of the relationship between the ocean temperatures and our weather is robust, is repeatable, and simulatable by a model which plugs in our knowledge of how the atmosphere works. And we can also tell how much of the weather that we get is inherently random, that's not determined by the sea surface temperature pattern. We measure that by how much variation there is from model run to model run, using the same ocean patterns, but different weather. So what we get, if you average all of the runs for each individual year, each dot here represents a particular year since 1950, and we're looking at rainfall, annual rainfall across the state of Texas on the vertical axis as a percent of normal, and the La Nina El Nino index is going from left to right. So anything to the left of the red line is La Nina, and middle part is near normal, then on the right-hand side is El Nino. And you see the same correlation that you get if you look at observations, where La Nina tends to be dry. On average, for a strong La Nina, you can expect 75% of normal rainfall, and El Ninos tend to be wet. Now, those are the averages of 85 different model runs. Now, if you take the wettest of those individual model runs for each of the years, you get something that looks like this. So that any ocean temperature pattern that we've had since 1950 is, in principle, perfectly capable of giving us a wetter than normal year. Every one of those dots is at or above the zero line. So a La Nina, as we saw this winter, does not guarantee a dry year. Just like a El Nino doesn't necessarily guarantee a wet year. Most dots are below the zero line if you take the driest model runs of each of the sets. So what's going on here is you get a wide range of possibilities. There's this correlation. You tend to have dry conditions with La Nina, 4 years out of 5. You tend to have wet years with El Nino. But within that, there's a large amount of variability that no amount of science is ever going to pin down. It simply depends upon the randomness of the weather, whether you happen to get lucky with storm systems or storm systems happen to develop differently. So the reason we have begun relying on La Nina as a seasonal forecast is because it's the only thing we know of right now that is usable in this sense, outside of trying to actually simulate the whole ocean atmosphere system. We're making progress in simulating the ocean temperatures, but that's only going to get you so far. La Nina turns out to be useful as a long-range forecast tool because, first of all, it matters. There is a fairly significant correlation. It does tell us something useful, not something that's guaranteed, but the tendency of whether it's going to be dry or wet. And also, it's predictable. You can tell by summertime, by midsummer, what sort of year you're going to have in the winter. At least what the odds are going to favor. So the other things that matter seasonally that are important but aren't predictable, things like the North Atlantic Oscillation, the location of the jet stream across the Atlantic Ocean. That changed a whole lot between last winter and the winter before, And if we had known what the NAO was going to do, we could have made a much better forecast, but NAO is not predictable beyond a couple weeks. So that's a matter of the randomness of the weather. Even if you get a snowstorm early in the season that dumps snow across the Midwest, that'll affect the temperature pattern, that'll affect the pattern of cold fronts, jet streams, and it has a long-term influence if it doesn't melt quickly. So all these things are random, which if we knew what was going to happen in advance, we could make a much better seasonal forecast, but it's simply not possible. So now let me turn to longer-term climate change. Because it's a similar sort of situation. There are many different things that affect climate. And climate, of course, has changes and always has changed. And I've got a list here. Some of them are new factors that man has had a big influence on. Others are perfectly natural. Solar variability, for example. Volcanic eruptions that produce particles in the stratosphere that block sunlight. Greenhouse gases that change how much energy is emitted into space from the Earth. Changes in the orbit that affect ice ages, and so forth. So these are all important for long-term climate, but unless we're going to live 10,000 years, we don't really have to worry about the Earth's orbit. We don't have an ice age coming up in the next few decades. But the others all are important on the time scale that we care about for planning purposes, for looking at water supply. But there aren't that many of them that are predictable. Solar variability, there have been no reliable 10 to 20 year forecasts of solar activity yet. People are trying to do that. We'll see how that goes. Volcanic eruptions, you can't predict the next spate of volcanic activity. That's not possible. You can't presently predict whether you're going to have an El Nino 5 years in the future or 10 years in the future. Maybe ocean modeling technology will advance far enough that in the next few years or decade that will become a possibility. And of course, the randomness of the weather, we're out of luck. So that leaves us three things. Greenhouse gases are really quite predictable. Even though we don't, to make an exact forecast, you'd have to forecast economic activity and then the climate response to that, and that's a bit of a challenge. But if you look at the record of greenhouse gases, those are going up steadily. It's the most steady signal you can find out there in the climate system. So I want to take a look at what's happened in Texas over the past century and what's projected to happen based upon the subset of climate factors that are predictable. So if we look at rainfall in the 8 regions of the state I looked at over the past century, each one of those lines is a different region. For the most part, they tell the same story, except for West Texas, which is not as upward trending as the rest of the state. But most of the state, we've seen an increase of about 10 to 15% in rainfall over the past century, which is a nice thing to be able to say at a water conference, as long as it's not a flooding conference. On the face of that very tendency, there's also some rises and dips. You see the middle part of the century when we had the drought of the 50s is a relative minimum. I've smoothed this out to look at only the multi-decade scale changes, so you won't see any individual droughts in this. You'll just see periods of time when things were relatively wet or dry. And the wettest period, the last couple decades, there's some evidence from triggering studies that this may have been the wettest 2-decade period in the past 500 years. And it would sure be nice to know whether that trend was going to continue. Unfortunately, we don't know haven't teased out the different causes for the increase, so we can't say whether that trend should be expected to increase. Based upon the set of climate factors that I talked about, climate models project pretty much steady rainfall or perhaps a slight decrease by the middle of this century. But the range is fairly small compared to the variability that we see, and the decrease is small compared to the increase that we have seen. So this is a fairly small potential impact compared to natural variability. And of course, anybody who works with water in Texas recognizes how big a factor natural variability is in terms of getting the drought cycles and so forth. And I don't have time to go into this in detail, but that longer term variability is very much tied to what happens in the Pacific Ocean. It's a well-established physical relationship that you have periods of time spanning multiple decades when the tropics tends to be cool and Texas tends to be dry. There's some emerging evidence that the Atlantic Ocean also has a big impact in the summertime, with the Atlantic being warm, leading to dry conditions also. It's not as solid, but there's a lot of supporting evidence for that. And basically, both oceans are working against rainfall in Texas in the 1950s and 60s during that drought period, and also since near the beginning of this present century. Now, for the general public, that's the end of the story as far as drought goes, how much rain we get. But there's another extremely important natural factor, and that is temperature. And I think people got a hint of how important temperature was to drought with the drought that we had last year. This is a plot of rainfall from left to right during May through August versus temperature. And each dot represents a different year out of the past 116 years or so. And you can see there's a pretty strong correlation. The wetter it is in Texas, the cooler it tends to be. And conversely, when it's dry, it tends to be warm. So we'll add 2011 to this plot. And it broke the previous record by 2.5 degrees Fahrenheit. You know, it's a hot day that breaks a record by 2.5 degrees Fahrenheit, and this is the average for the 3-month period, June through August. And the consequence of that was we saw rapid evaporation of water from lakes. We saw decreased runoff because water was evaporating rapidly from the soil and from streams. At the same time, plants were undergoing stress and were requiring more water to survive and grow. So temperature affects everything that happens to water once the rain reaches the ground, between when it reaches the ground and when it actually makes it into the pipes toward the faucets. And what we see for temperature over the past century is a lot of variability also, and not much of a long-term trend, except for the past few decades or so where since the 1970s temperatures have increased fairly rapidly by, depending on part of the state, between 1 and 2 degrees Fahrenheit. And I plotted here the climate model projections, which show basically a continued increasing trend at roughly the same rate that we have recently experienced. Now, to go back to my point before, this is only 3 out of 7 or 8 different factors, and there's a lot of other things that affect the climate. First off, the uncertainty that's shown here is based on the range of climate models. There is expanded uncertainty if you consider the range of possible emission scenarios. And then you expand the uncertainty even more based on we not know whether the sun's going to become more or less intense. We don't know whether volcanoes during the next half century are going to be less active than normal or more active than normal. So really there's a wide range of possibilities, ranging, I suppose, from something, temperatures being in mid-century, something near what we have right now, to the average temperatures in mid-century being similar to what we had last summer. So this is the big uncertainty as far as I'm concerned in terms of future water supplies. We can project population increases, but temperature is still a big unknown. Certainly, it's hard to imagine a scenario where temperatures are going to decrease, and we have to be really lucky for them not to increase substantially, which means more evaporation, less water availability as a consequence of that, and other potential implications such as importance of using irrigation systems that don't have water passing through the air onto the way of the root system, storage underground, which is not subject to evaporative loss and that sort of thing. So to summarize, right now, we've got two oceans working against us. We've been in this drought period where we've seen several frequent droughts over the past decade or so, which means we're in the drought susceptibility period, to which my reaction is, oh no. We can't predict when it will end, but presumably we're past the midpoint based upon how long the past few periods have lasted. So cross our fingers on that. Rainfall will increase, or is very likely to increase over the next couple of decades as a result of that. However, temperature is also likely to increase, and that temperature change is not part of a cycle, but is part of what we seems to be a steady rise with no sign of stopping, which means more evaporation, more water demand, less stream flow, and consequently, the same amount of water won't go as far as it used to. Thank you. Happy to take questions.
We're lucky we'll be doing as well as we are now. If we're not lucky, we'll be in a much more disastrous situation.
Yeah, I think that's fair. If we're lucky, we'll have the same. Have the same amount of water delivered to us and available to store as nature has been providing. But if not, I mean, the odds favor becoming drier because of the rising temperatures. And going back to what I said before, that's not the main driver of the imbalance between supply and demand in the future, but we're talking about potential impact of 10 or 15% on that order, which is important because it's on the margin. The cheap things that we can do, relatively cheap, take care of the increasing population to some extent, but the 53 billion doesn't include the additional requirements for water because of potentially warmer temperatures.
My name is Larry Hoffman. One thing that I don't think I heard you talk about is carbon dioxide emissions. And as I have tried to learn about global warming and the impact of those kinds of emissions on climate change, I've sort of concluded that CO2, which represents about 3/100ths of the carbon dioxide that's emitted totally, that's not much of a factor. But I wondered, do you have any opinions about whether we really need to worry about CO2, which is not a pollutant, but which is a fertilizer in which plants need to live? Is it really a factor, looking at the variations that we see here, and we know that CO2 has been increasing, human-emitted CO2. Is it really the factor that a lot of people say it is?
Well, certainly CO2 concentrations, as well as nitrous oxide, methane, and other important greenhouse gases, are increasing and increasing steadily. So from the point of view of climate projections, it's sort of beside the point as to what the cause of that is. We still have to deal with it no matter why it's happening. Now, to get back to and furthermore, whether or not it's an increasing CO2 is good overall, if you balance the benefits and disbenefits, is independent of its impact on water supply. But to answer your question directly, most of the carbon dioxide emissions to the atmosphere from the ocean and from plants are cyclical, such as equilibrium between atmospheric concentration of CO2 and ocean concentration. And that balance is a long-term balance. The problem with the small increase of emissions beyond that is it's not balanced from something. It's similar to the study that came out recently about sea level rise. where a large portion of sea level rise is actually due to aquifer depletion. Now, the aquifer depletion is a ridiculously tiny amount of the amount of water that flows into the ocean. But it's a part that's coming from a source that doesn't get replenished. And consequently, it adds to the overall amount, whereas the other inputs don't produce a net increase. Yes.
Two things in regard to what you said about the increasing evaporation. First, I believe I just heard you say we really need to move to subsurface drip irrigation.
I'm sorry, I can't quite hear you.
We need to move to subsurface drip irrigation away from spray systems. Did you essentially say that?
I said the benefits of such a move would increase with time.
Okay, and then the second one is, due to the increasing evaporation, will we be better off to intercept and use water closer to where it falls, such as rainwater harvesting systems, instead of the large-scale systems that we use now that use lakes and rivers for cisterns?
Yeah, that as well would have an increasing benefit as temperatures increase.
Thank you.
Good morning. Tom Weber with Travis County. One of your last slides showed some box plots and I guess the percent change of temperature of rainfall in the next several decades. And I believe that showed Texas as an average. I was wondering if you had a line between East Texas and West, would you expect those increases to be greater than that average in the West or less? Of course, I think of West Texas as upstream of our dams, so that's an important factor. Any comment on that?
Yes, it is. With the model runs that I showed, those are based on the what's called, they're the runs that went into the 2007 IPCC report. And there was not a strong pattern to the rainfall changes averaged across all models. Some models said there'd be significant drying in West Texas and East Texas do fine. Others said the opposite. So it was quite a mixed signal compared to, say, the clear signal between Mexico itself becoming quite a bit drier and the northern United States becoming wetter. I do not know, I haven't looked at the model ones that are just now coming out for the benefit of the next IPCC report, but based on the rate at which modeling is improved, it's probably not going to be a much clearer signal either. Now, that's not to say that, another thing I didn't mention, which will matter, I think, in the context of your question, is that the impact of temperature is not necessarily going to be uniform, even if the temperature rise is fairly uniform. Because central part of the state, where you're dealing with a big difference between, a close balance between rainfall and evaporation, that's going to tilt toward the evaporation side increasingly. In West Texas, everybody's used to evaporation and they deal with it. In East Texas, don't really have to worry about it much because there's plenty of rain, but I think in Central Texas is where it's going to matter a lot.
Have you read any information or had any information exchanged with the weather modification technology that's being used in Moscow, the so-called ionization towers and their ability to affect the formation of clouds and so forth? Is that any credibility to that, anything that you're aware of on those studies?
I haven't seen anything credible in that regard, mainly because of the mismatch between the size of the particles produced by that and the size of the particles needed to form cloud condensation nuclei. Conversely, there's nothing to say that there may not be some not well understood process in between that allows it to work, but it's very difficult to prove it in the field because rainfall is such a random process, and consequently without having a solid physical connection, theoretical and laboratory, from in process to rainfall, is difficult to put much confidence in it.
Thank you.
Bill Brinkley, how does your data correlate with the potential rise in the levels of the ocean and melting of those polar ice caps, the changes that are anticipated along our shorelines?
The changes in sea level rise across Texas is sort of like the climate and water supply. It's not the main driver. Coastal subsidence in Texas is a bigger influence on sea level rise than increasing global sea levels, but it's a significant factor on the order of a third of the net change. All indications are that that's going to be a gradually increasing trend. There's even the prospects of a rapid increase of sea level rise. Still, rapid by rapid we mean several decades rather than several months. But it's the sort of thing which, like carbon dioxide, shows no sign of slowing down or decreasing. So it's something that coastal communities will gradually have to deal with. And it gets felt primarily not in the day-to-day sea level, but the more catastrophic events such as hurricanes that produce storm surges, which are just a little bit stronger and a little bit higher than they used to be.
Thank you.
You didn't say a lot about population. In 53, 4, and 5, the state was, what, 7 million, and 70% rural and 30% urban. Now we're 22, whatever, and just the opposite. So that's got to figure in this. I know the San Antonio presentation talked about looking at the future. So your observations about that. And the second question is, at the airport in College Station, the temperature last year was exactly 2 or 2.5 degrees than 6 or 7 miles from the airport. Now, I don't know whether there's more hot air there at that spot, but if that's the number you take, it's surrounded by concrete. They've added more concrete out there, but as we took the temperature away from there, that wasn't the, it was hot. It was hot. It was dry. Everything was burned up. But those readings are coming from those spots that aren't, and then well, I'll stop there. But I'm interested in how those numbers are being taken, and you know, because you were exactly up on that chart, which if you go to the Brazos River, it wasn't that temperature, just a few miles away.
Right. Yeah. Yeah. Locally, for example, at Easterwood Airport, you have runways, but you also primarily you have fields and unirrigated oak forests, whereas in the Brazos River, that's even during the drought, it was receiving water from irrigated cropland from the river aquifer, and that has a big impact on local conditions. During a drought, in fact, we tend to see that many cities end up being cooler during the daytime than the surrounding areas because people are watering their lawns, whereas nobody's watering the forests and fields. In terms of where the data I plotted comes from, I didn't have time to go into that, but that was based on what's called the United States Historical Climatology Network. There are 48 stations within Texas. About 3 of those are airport stations. Most of them are rural. And the fact that you break them into 8 geographic regions, and they all show the same story, supports the idea that it's not a few airport stations that's giving that signal. And back to your original question, yes, climate change is not the big thing to be concerned about. My main message is here, it's not to be ignored either.
It's Mark Pearson. Question about your 7 or 8 factors that you kind of struck because they don't affect predictability or they're not useful for predictability. Do you have a quick way of talking about what those look like in magnitude and duration as compared to the part that does go in the model? Like, because some of your variance in the model is the different models, some is change in emissions. How does magnitude of that compare to what those other factors look like when they do happen?
We're out of time, right? Yeah, that one takes a long time. We try to break the uncertainties down into uncertainty in the forcing, the changes in the radiative balance, and then uncertainty in the response, which involves climate feedbacks. And for the most part, the scientific consensus is that the feedbacks will predominantly be independent of the forcing. In other words, no matter how you bump the climate, if you make it warmer, there'll be more water vapor, and that's a positive feedback. Clouds will be affected, whether you warm it by one mechanism or another mechanism, and so forth. Most of the uncertainty there is well, as I mentioned, well, no, I didn't mention it. I would say that the uncertainty in the feedbacks, and therefore the response to changes in aerosols and CO2 and other greenhouse gases, is larger than the uncertainties in the forcing are likely to be. And there's a little footnote on that. We've had times in past, including geologic history, where we've had volcanic activity much larger than we've seen now. So it's possible we'll have a volcanic catastrophe that'll make the Earth colder. But based on what's happened over the past 1,000 years, it seems like the forcing, the forcing uncertainties are fairly well pinned down, and it's the feedback that's going to be the main thing scientists have to make progress on.
Perhaps you can talk to John afterwards.
Oh.
Okay. Thank you again, John.